So thank the organizer for the opportunity. So I will talk about the relationship between Gibbs measure and G measure. And as you see in the title, so there's a spoiler here. I will talk about that the Gibbs measure of the Dyson model is not a G measure. So let's talk about it. So first of all, let's set some definitions. First, let's consider G be an infinite connected locally finite graph. Lambda is a finite subset of G. Omega lambda is the set of string configuration. Omega is the configuration of the set, and the tau is the boundary condition. And we are considered the natural sigma algebra generated by the cylinder sets. So let me define the interactions also. So this is a collection of the fx measure of function over all finite set x. Hamiltonian is the natural way to define it, the sum of all the energy of sum of all interactions. So the Gibbs measure on the finite volume lambda with inverse temperature beta is defined in the natural way. The exponential of minus beta times the Hamiltonian. And the z is the normalization factor, is called the partition function. And we can also define the Gibbs measure on the whole infinite volume for all G, for whole G by using the DLR equation. So these are just a natural definition of the Gibbs measures. So now let's define the G measure. For the G measure, we should define only for G equals to Z for the integers. Let me just write here. And the G measures, first of all, let me define what's called G function, or just a function. A G function is some function that satisfies two things. So one of these is continuity. That is can define because a natural way, because the product topology of the -1, 1 on the integer, in this case is the non-positive set is metrizable. And let's also say that the strong positivity. So this means that the function G is very far from from 0. And the G measures is just a probability measures that's continuous, strongly positive, and satisfies this equation. So this somehow says that the probability measures is associated to this G function, this G. And well, there's some definition that is less restrictive. Instead of the continuity, we can assume just the measurability. Instead of strong positive, it's also possible to define only by positivity when G is larger or equal than 0. And well, let me just say one type of natural question. So Gibbs measures, we can define the Gibbs measure by the following thing using the thermodynamical limit as well. So if we fix a boundary condition here, let me use the tau here, and take the lambda, the limit of lambda thermodynamical limit at both sides. So for some type of boundary conditions, we have a thermodynamical limit, so the Gibbs measure at the whole z. And the G measures, it's also possible to see it by freezing some configuration here. Let me use tau here. So this quite means that we are considering the finite box, and we just taking the thermodynamical limits on the right, keeping the left. Well, this is somehow actually is possible to define more formality using the global specification, but I will skip about it. So since the definition of the Gibbs measure and G measure is quite the same, it's quite similar, so it's quite natural to ask that if the Gibbs measure and G measure are equivalent. So first result by Fernandez, Gallos, and Maillard, they prove that there exists a G measure that's not a Gibbs measure. So one of the implications is false. And they prove the existence by construction. So they only constructed some special type of G measure. They prove that this is not a Gibbs measure. And we prove that there exists a Gibbs measure that's not a G measure. And this Gibbs measure comes from the Dyson model. So Dyson model is the ferromagnetic easing long-range interactions where the interactions decays polynomially with parameter alpha. So this is the Hamiltonian of the Dyson model. We were considering the ferromagnetic case. So note that we know that for easing the nearest neighbors case, for the classical easing model, we don't have phase transition at any temperature on Z. But in that case, for the Dyson long-range interactions, we have a phase transition at low temperature. So this is the result. We have proved that the result says that the Dyson model at low temperature is not a G measure. So with more formal results, we are considering the following things. So alpha plus is just this technical number, this strange number, 3 minus log 3 over log 2. And so we prove that the none of the Gibbs measure mu of the Dyson model at sufficiently low temperature is a G measure. But note that there are two things here. Alpha, the parameter alpha of decayments should be between alpha plus and 2. And note that this 2, alpha, we can't prove for alpha equals 2 as well so far. And another thing here is that only for at sufficiently low temperature. So this quota means that it's very far from the critical temperature. We don't know what's happening close at the temperature, close at the critical temperature. Okay. And what we proved that this conditional probability given the past is essentially discontinuous in the alternating configuration. That we will see this. So let's see the proof. To use the proof, we should use some tools. One of the tools is using by so-called contours, using contours on Z. First definition of contours on Z is by Froelich and Spencer. They define this contour on Z for Dyson model with alpha equals to 2. And they prove phase transition using somehow classical Pyre's argument. And after this, Cassandro, Ferrari, Mirora, and Presutti extended the definition for any alpha between alpha plus and 2. And we should also suppose that the energy of the nearest neighbor should be large enough, but for some technical way. So here appear why appear this alpha plus? Because of the definition of the contours and of the argument about it. Right? And after that, Littin-Picot proved the phase transition using counter-arguments and extend for any alpha between 1 and 2. And also still suppose that the energy of the nearest neighbor should be large enough. So let me just say one thing. So tomorrow, Littin's here. So tomorrow, Littin will present by a poster about these results. So they proved somehow this result using proving the quasi-additiveness of the Hamiltonian of the Dyson model. And let me just say one of the parallel results. If you consider the Hamiltonian with the non-homogeneous external fields, where the external fields decay also polynomially, and first of all, note that for this Gibbs measure, this Hamiltonian is non-translation invariant. And let me just suppose that there exists another alpha star here, just another technical things. But most important thing is that the alpha star is between 1 and 2, and this alpha star is larger than alpha plus. So we prove also that the Dyson model with exponents alpha between 1 and 2, including 2, and if we take gamma, the exponential of the non-homogeneous external field, is larger than the maximum between this alpha star minus 1 and alpha minus 1, we undergo the phase transition at low temperature. One important thing here, now, using this fact that this alpha star, so this means that if we reduce a bit the interval of the alpha, so we can assume that the energy of the nearest neighbors can be small, can be equal to 1. Do not need to suppose high enough. Right, so. Another main tool to prove this the lack of the continuity, we use the notion of interface point on Z due by Cassandro, Mirora, Picot, and Rozkov. So let me just say a bit what means this interface point. So let's consider on Z Dobrushin boundary condition. So on the left is R minus, on the right is R plus. So take this interval very large enough. So near this minus boundary condition, it's quite expected using the fact that we are considering a ferromagnetic case, that the magnetization here is negative because they are very close to the minus boundary condition. And the same things happen when we are close, all the spins all the sites that's very close to the plus boundary condition. So here the magnetization is positive in that case. So note the first thing. So here we are, we say that this is a minus phase and plus phase. So on the left we have minus phase, on the right we have plus phase, going to the close and closer. So this means that there exists some point here that we have a transition between minus phase to plus phase. So this point is called the interface point. So this is somehow the heuristical definition of the interface point. Okay. And one important thing that we should use here is that the fact that if alpha is between alpha plus and 2, excluding 2, the inverse point is located mesoscopically. So this means that for alpha between these two numbers, the region of inverse points increases as this large interval increases, but should increase slower than the large interval. And another is the macroscope means that they have the same speed. And here this somehow means that the y alpha equals 2 is quite difficult to prove with our case, because we should suppose that the interface point, you should have the fact that the interface point is located in some mesoscopic interval. So we should have some propositions here. One result is the phase separation. This means that if you take n large enough, so take some L, very large, and take L extremely large enough, if you freeze this interval by minus, so this is frozen minus interval, this means that all the spins near these frozen minus intervals has minus phase, somehow because of this, quite the same argument as this one. So this means that we can somehow control the region of minus phase if you take n extremely large enough. Another important thing is the finite energy of the alternating configuration. So this means that if you consider the energy of the alternate configuration inside of some interval with length L1, and if you see what's happened with this energy compared with the outside of this interval, so the energy, this energy is uniformly bounded. So this means that if you take L1, if you increase this L1, the energy of the alternate configuration cannot increase large enough. So that's the sketch of the proof. So this is only with this picture is enough to prove somehow they prove the result. So this means the following. The proof is done by following. Take this 0 here, and take minus L1 here. And so let's take minus an interval with length minus L extremely large enough, and let's freeze by minus. Let's see the second picture. So take n very large enough in order to the origin has minus phase. Of course, we can take some interval of minus phase, but let's see just at the origin. So the origin has minus phase. This means that the magnetization is negative. And using the fact that the alternate function has a finite energy, this means that adding a alternate configuration here, the alternate configuration is weak enough to change the phase of at the origin. So they still have minus phase. The same thing happens when we freeze by plus interval here. So in that case, the origin has plus phase. So note the following. If you take L1 large enough, in both things, and take n of course, very large enough, we have two sequences here that convert to the alternate configuration. But for this sequence, the origin has plus phase. But in another sequence, the origin has minus phase. So we have lack of continuity here, proving that the Gibbs measure of the Dyson model cannot have a property of the continuity of the G measure. So it is not a G measure. So this is the proof. That's the reference. So we use that's the reason that we use it. And also we use the result of Lichten-Pico for the case of non-homogeneous external field. Well, that's it. Thank you very much.